Good morning to everyone. Today we are going to discuss the Discrete Mathematics Unit 3, which is a jntuh syllabus. The topic we are going to discuss is strong induction. The student already know the mathematical induction. You can think like it is a advanced one of the mathematical induction. So first we'll come to the definition, then we'll see what is the difference between mathematical induction and strong induction. P of n be a statement which we want to be proved. So strong induction we can divide into two parts. First the basis step. So what is the basis step is we have to prove P of n is true for n is equal to 1. The next is the second part, inductive step. So what is the inductive step means? We have to prove P of n is true for n is equal to k plus 1, assuming that P of 1 and P of 2 up to so on, P of k is true. That means P of 1 is true, P of 2 is true, up to so on, and P of k is true. Take P of 1, P of 2, P of k is true, and we have to prove P of n is true for n equal to k plus 1. So now what is the difference between mathematical induction and the strong induction is, in the mathematical induction, as we assume statements true for n equal to k, and we can prove for n equal to k plus 1. In the inductive step, in the strong induction, proving n equal to k plus 1 not only depends on k, it also depends on its previous steps. So that is the difference between the mathematical induction and the strong induction. If you know k, we can prove k plus 1. If the statement is assume k and you have to prove for k plus 1 is mathematical induction. Proving k plus 1 not only depends on k, it also depends on previous steps p of 1, p of 2 up to so on. Then it is called as a strong induction. So this we can write in another way, like a conditional statement p of 1 and p of 2 and p of 3 up to so on, p of k implies p of k plus 1 is true. That means we have to prove the conditional statement p of 1 and p of 2 implies p of k plus 1 is true. So it is like a conditional statement p implies q. So now next we will see about the one problem, how to prove this. uh, strong induction. So now problem question, show that if n is an integer greater than greater than 1, then it can be written as product of primes. If the question is show that n is an integer greater than 1, then it can be written as a product of primes. So now what we are going to do means let P of n statement that n can be written as product of primes. So now first basis step. So now basis step is we have to prove for n equal to 1. Prime starts from number 2. So we go for 2. N equal to 2. 2 can be itself as a product of prime you can be itself as a product of prime 2 only. That is P of 2 is true. P of 2 is true. Next step. So in the inductive step, what I'm assuming is P of j is true for all what I'm saying is for all less than or equal to j less than or equal to k, p of j. That means the statement is true for all the integers between 2 to k. Basically, in the mathematical induction, we assume n equal to k. Here, I'm assuming not only k, I'm assuming all the numbers k less than k also up to 2. So now, wait a minute. Now, we prove p of n is true for n equal to k plus 1. Here the two cases arise. If k plus 1 is prime, then there is nothing to prove. If k plus 1 is not prime, then the case arises if k plus 1 is not a prime. That means k plus 1 can be written as product of composite numbers. So now k plus 1 is equal to sum a into b. A into b. So now where a b are the between k, k plus 1 can be the product of composite numbers. The composite number means, for example, 8 is a composite number, 9 is a composite number. For example, 18 is a composite number. So 18 we can write some 6 threes are. So whatever this e comma b, they are between 2 to k. But just now you assume q of j is true for all 2 less than or equal to j less than or equal to k. Means every number between 2 to k that can be written as a product of primes. Here a comma b, here a comma b are also between 2 to k. Therefore a comma b can be written as product of primes. A comma b written as a product of primes, which implies ab can be written as product of primes. AB is written as a product of prime, which implies k plus 1 can be written as a product of primes. Therefore, by strong induction, every integer greater than 1 can be written as a product of primes. Then the statement. Statement P of n. Thank you. Thank you very much.